Hello, today I'm going to talk about thermodynamics in chemistry. At first, thermodynamics is used in various domains of physics. Um, it's interesting because it's used to study different things, such as thermic machines, with the work of Sadi Carnot, or chemistry reactions. Um, Also, you can find it in some useful places, like when you study sound waves with the coefficient of isentropic compressibility, known as Xi. Basically, what it means is that when you fix entropy, you can define a coefficient that is dependent of the, the variation of the volumic mass based on pressure. It's kind of complex, but it's really interesting. You can also find it on the study of plasmas, because plasmas are very dense gas that collide with each other, so you need the thermodynamic formalism to solve it. Also, I wanted to say that chemistry is a small part of physics. Physics scale is from subparticles to the whole universe, while chemistry is from one atom, maybe a few electrons when you do atomistics, up to a few moles, maybe 1 liter at best. At first, to understand thermodynamics, you need to define a few scales: microscopic, mesoscopic, and macroscopic. Microscopic is the scale of the, the particles, subparticles, electrons, atoms at best. Mesoscopic is when you can define state functions. So it's small enough to define differentials, but not big enough to define differentials, but not big enough to like apply macroscopic scale. And macroscopic scale is what you measure. It's a mean value, and if you do quantum mechanics, you study that. Well, I'm not going to talk about quantum mechanics. Um, so what you often study is in chemistry is equilibrium. It's the fact that no state function will vary um, at after a certain time in time. I mean a certain time after you did the reaction. So this will be very important because it does not apply to only chemistry reaction, but also um, physical and nuclear reactions. Principles of thermodynamics. The first one states that you can split energy into two parts: heat and work. Okay, so um, this is very interesting because in mathematics you're not allowed to like split up um, place terms, but in physics you can sometimes, and in this time it works. Um, about these are differential writings, which is why there is a D. Oh yeah, and also it's not a D, it's a delta. Oh well, uh, it's a delta. Yeah. Okay. Same for there too. It's a delta. So the delta double V, double V is work, differential work. It means the forces around the system will make the stuff move, and that will be a part of the energy. It's really easy to define. Later we'll differentiate pressure forces and non-pressure forces in this term dW. But what's very catchy to get is delta Q. So it's a differential of heat. It used to be called thermic with thermic fluids terms in 1800s. Um, but people aren't still sure how to define it. So I have few um, definitions for you. Heat is either the energy part linked with thermic exchanges, and another definition that was given me was that it's the part of energy that is not linked with the work of forces. So it's kind of fun because both means nothing. Because like if I say that Q is the thing that is not forces, not the work of forces, it's just this law. So yeah, you can either define it. I heard this as a definition for Q, so it can work. Or you can say that it's thermic, the term that is based on the the temperature. The second law is that you can define a function named S. What it defines is the local disorder of something locally, and I purposely use the word local twice. So imagine you have uh, a few sets of strings that are elastic, and actually you can modelize atoms like this and some other particles interactions. But okay, imagine you have few sets of atoms with elastic strings in them. If they aren't excited, they will stay at the mean value of the elasticity, like they will stay in group. But if you start moving one of the atom with the at the side of an elastic string, it will start moving the following, and that will create some sort of moment of movement, and that's how we call entropy. And you differentiate it from global disorder, because it's not the same as having a molecule agitated and just an atom agitated. It's kind of different, because imagine you are on a party. If you are the only one dancing and none of the around you is dancing, it's not the same as if everyone was dancing with you. Um, it's kind of complex, but I guess that's a definition. And that differential S for entropy can be split in created and exchanged. Oh, there is a D, I suppose, here. Um, Terms. So the entropy created can look weird, but that's how it works. Entropy increases. That's this law. Um, I can't demonstrate it, it's too hard. But entropy exchanged is the entropy exchange with the, the other um, uh, reactives, and that's mainly what we study. We often don't study that part here. It's too hard. And the third one is the normalization of entropy, which states that in some cases S equals 0. It's not a fundamental truth of a reality, but it's used to like do some calculus, but it's useful. You can split energy as a sum of internal energy, dU, and kinetic energy, dEc. Um, and what we'll often study is dU, because kinetic energy comes from other systems usually, or can be defined, while this is just the material on itself. The differential work of forces, forces of pressure, is minus P dV, so minus the pressure, the differential of V. That's a law. Okay, now let's define enthalpy. Enthalpy H. Enthalpy H is a variable that you will Legendre transform from U with PV, and that you can approximate to H more or less equals to U plus PV. That's very interesting in physics that you can do that, because it will, okay, I'm not going to talk about the mathematical impact of the Legendre transform, but basically you will remove the part of the pressure and bring another term that's really interesting, that you can add the term to another with the Legendre transform. Okay, let's talk about the perfect gas model. The perfect gas model is a model where you neglect the interaction between atoms in a gas, because a gas is a very small density of atoms, so the probability they collide is actually really small, and they will not slow down much as if it was on a heavy gas like in plasmas. So the perfect gas model, you'll use three mainly constants: the constant of perfect gas, the Avogadro constant, and KB, the Boltzmann constant. Linked with this, PV equals nRT, P pressure, V volume, N equals the number of the number of atoms, RT is R the constant of perfect gas, and T the temperature. du differential variation of internal energy, equals C and CV dt, and times n. Sometimes it depends how we define CV. CV is actually a constant that you use to define this relation, and basically it says that it's constant on this relation. You can use it in lots of calculus. There is this property. CV is a constant divided by 2 times nr. In perfect gas, this constant is often 3 on 2, but you can also find 5 on 2, and at very high temperature you can find 7 on 2. It's actually linked with how matter is linked with the strings, as I told you earlier. With 3, there is 3 ways to move if there is only one atom. If there are 5, they can move in 3 directions plus have um, um, a, link between them with rotation. And at very high temperature you can have torsion between the links, like the links between the two atoms will start to distort. dH equals n Cp dt. It's the same as before. CV is defined as at constant volume, or isocore in French, and CP is defined as at constant pressure, so isobar in French. Use this relation. Also, there is a gamma that is a constant. And it's Cp on CV, and I forgot this law. PV times gamma times gamma is constant. That's the law called law of Laplace, and it states that for perfect gas, obviously. You also have the relation Cp minus Cv equals nr, it's a basic property. C exchanged equals the sum of Qi on Ty, so Qi the heat and Ty the temperature, E being the studied things on the system. Yeah, entropy increases as created superior or equals to 0, and it's equals when it's a reversible transformation. That's the definition of reversible transformation. There is this relation that defines S with KB and microstates omega, but I'm not going to talk about it much. There is this relation called the Clausius relation. It states that you can't have a perfect D-thermal machine. There is the law of Arrhenius, K being the speed of the reaction equals a constant. Well, you can detail this constant, but we're not going to do that today, even though it's chemistry, but it's not very linked with thermochemistry, but more cinetic, but okay, it's kind of different. It equals to a to the exponential minus the activation energy. It's kind of complex because it's the energy required for an atom to shift states divided on R times T. Okay, this is very interesting. The density, the volumic density of thermic flow. In physics, there are many laws that looks like that for particle diffusion, for electricity, but it works for thermic flow too. So it's like the diffusion. It's the global things for diffusion. You have a vector that equals to a constant times a gradient. The gradient is also is this thing, like this part on a vector on Cartesian base. It's the partial t on x, y, and z, like this. So this is used in many fields of physics, the gradient, the gradient, yeah. So grad of t equals nabla of t, and it's like this in a Cartesian base. So yeah, it means that the density of the flow in the volume is given by this. The flow, that's the flow. It's defined like this. It's the integral of the density on the ds being the infinitely small surface on the system. Well, it's not on the system technically, it's a surface, so, but I wanted to make a surface that you study. This is mainly used for physics, but it can be useful. Like, for example, if you have a river that has more or less um, heat and you are putting a chemical reactive on this, and you will have values based on space. So you will have equations based on space and also other things. So that can be interesting. The thermical resistance. So maybe you have seen that in your electricity lessons, how to define the resistance. There is the same equivalent for hydrodynamics and also for thermodynamics, because this is the resistance thermodynamics. It's the variation, it's defined as the variation of temperature divided by the flow. the thermic flow, the more the more it resists to heat, exactly like resistance in electricity. So here I'm going to define the writing of nu I. It looks like a V, but it's not. It's the letter nu, like this. So if you have a chemical reaction uh, A times product reactive A plus B times reactive B, um, chemical reaction with C times the chemical reaction C plus D, blah blah blah. You can write it like this. It's not very equal, but like you can view it as this, with nu being negative when it's on the other side of the equation. So yeah, sometimes this thing is negative, so beware. Use this law to define the delta underscore R. It's the sum of the thing on the reaction, with this being the stoichiometrical coefficient, times the thing 0 and I, 0 being in few condition and I being the considered reactive or product. You obviously use it for H, the enthalpy, enthalpy, and you find this law. And actually, there's another law called the law of S, and this is actually very, very useful um, for the calculus, because it gives interesting exercise about endothermical, exothermical reactions. So they give you this, the delta F H of a species. It equals 0 for pure corpses, and it gives interesting things, like you can determine if the reaction is endothermical or exothermical. So it's kind of cool. The thermic capacity with fixed pressure per unit of mole, CPM, it's actually the molar enthalpy on temperature with fixed pressure. If P is constant with closed system, we obviously find this, because as I said, it's the delta H is the Legendre transform of the U with the term of pressure stuck, like in the Legendre transform, and since P is constant, the V dP, V times dP is 0, because dP equals 0, so VdP equals 0, so you have this. Delta H is the integral of this. It's more or less an application of the law of Hess. Okay, now let's define the free enthalpy. So it's the Legendre transform of H and minus Ts. Can approximate it by H minus Ts. This will be useful to define things with temperature and entropy. I'm going to explain it just after. So dH equals delta Q, delta heat, plus VdP, as I said earlier when we said constant pressure. If P constant, so dP equals 0, so this term was 0. And as we separated the terms from pressure, there is the work of forces that aren't pressure forces. So we have this expression. We can rewrite it like this: dH equals TdS plus VdP. VdP minus SdT minus T delta S created equals dG because it's G is the Laplace transform of H with minus TS. You have the term that simplifies, and you have this dg. Dg is always negative or zero by we stated already by the closures relation. Well, technically it's the reverse. Like you prove that dg is negative, and it gives you the closures relation. But yeah, you can view it as the system always goes to dg equals 0, and if not, it goes to dg negative, because if dg equals 0, it means that there's equilibrium, and if not, dg negative, always. Always, always, always. Let's define chemical potential. We have mu again, mu I, so mu of the species, equals partial derivative of G on Ni, so Ni being the species, when, with temperature, pressure, and other quantities of other species fixed. So it means that no matter how you put, this will be how many of the species you put, you'll always have this guy constant. For example, if you multiply the things you put in the chemical reaction, this will stay constant. So you can rewrite dg like this. So we just use the previous relation here and just rewrite it. We define delta Rg as the derivative of G on Xi. Xi is the avancement in French, in mole. It's the unit is in mole. It's how the reaction goes um, when you do um, when you study reactions, you'll see how far it goes. Sometimes you study if it goes to equilibrium. Sometimes there is not enough reactive to do it. So how to solve this? How to solve this kind of problem? First, you suppose that you have enough reactive to go to equilibrium, and then you calculate how it will go, and then you backtrack and verify that you have um, enough reactive to 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 do that, especially if you have chain reactions. Or you can suppose that you have not enough of the product, and suppose that there is a limited reactive. So yeah, that will be useful for that. You can rewrite d uh, d like this. Um, in the approximation of Ellingham, you can write it like this. It's not a definition, not a definition. The definition is this, and the 0 means in usual conditions. So P equals 1 bar. Yeah, I didn't say it earlier, but when there is the 0, it means at 1 bar, so at almost constant, at the usually Earth pressure. Where was I? Where was I? Approximation of Ellingham. This, the law of I can't pronounce it right. The law of Guldberg and Waage states that the constants of equilibrium equals exponential minus delta Rg 0 divided by RT. Yeah, we know that delta Rg equals RT ln Kr on K. Okay, this is a bit complex. It states that if the equilibrium is not reached, so if Kr is not K, it will go in the sense opposite to the dxc. So, so the variation, can view it like this, was minus dxc, like this. So the dg will always tend to is the thing that states that um, the difference between the current relation, the current state of your system, and the state it should have at equilibrium. And at equilibrium, dg equals 0. So delta Rg equals 0. So this equals 0. So ln this equals 0. And so yeah, so this is equal. Well, no, technically it's 1. Yeah, because you derivate on xc. So yeah, Gibbs-Helmholtz relation. Yeah, it's very easily demonstrable, but it's this. I should have maybe wrote the demonstration, but it can be boring for some. You have this huge derivative at fixed pressure, the derivative of g divided by t, uh, um, derivated by t equals minus h divided by t squared. And finally, the best of the best, the relation of Van 't Hoff. This is the relation, and we're going actually to demonstrate it. Demonstration. Delta Rg equals RT ln QR divided by K. Delta Rg0 equals RT ln 1 on K, because the like we derivate we study a case where it's not equilibrium. So we have delta Rg0 equals minus RT ln K. Gibbs-Helmholtz relations gives us this. We derivate this on Xi, and by the Schwarz theorem, we can swap the derivatives. Same goes here. Only K is dependent of T in this relation. Inverse the T, but you'll do that and you'll see. K in this, obviously there's the T here. Why did I write? Wait, why did I write this? No, it's L. Only the. What did I? What did I meant? It's. It will. You will get RT ln the K is dependent of T, so the T will go out, and you'll get what you'll get. And so you go down. And you take this relation, you replace the dxi of this by swapping, and you get delta Rg 0 on t um, divided by derivated by t equals minus r t, but t was in this relation, t was derivated by t by t, so you'll get this, and you'll get this. The other terms cancels out because it's divided on t. Yeah. So you get this relation from here. You have the minus h divided minus differential h on xc divided by t squared. It gives you this relation. And finally, you conclude you divide both sides by r, and you have this relation here, and you have finished. You have the law of Van 't Hoff proved. So you can now pretty much solve every single problem of thermodynamics in chemistry with little bonus of physics. So I hope you liked it, guys, and thanks for watching.